In this video, we'll learn how to factor special products. To factor special products, we first want to know what are those special products. The first one is called difference of squares. You'll know if you have a difference of squares if the first and last terms are of the form a squared and b squared. That is, they are terms that are perfect squares, like 25 or 49 or x squared, something like that. The operation symbol must be subtraction, or it is not considered to be a difference, because difference means subtraction. The other special factoring we'll talk about is the perfect square trinomial. So a trinomial is a perfect square trinomial if the first and last terms again are of the form a squared and b squared, so they need to be perfect squared terms. And the middle term needs to be 2 or negative 2 times the product of a and b. So I'll show you what that looks like in a few examples. In example 1, we're given x squared minus 36. So I see that there are only 2 terms, so it might be the difference of squares. We do have subtraction, so that's helpful. And then consider the first and last terms. X squared. That is a perfect square term because x multiplied by x, those are identical factors, are the only way for us to make x squared. And 36 could be written as 6 times 6. So 36 is also a perfect square. So the way these will factor is into 2 binomials, no gap in between here. We're going directly to the answer. And we're thinking of the square root of these terms. X squared is the factor x times x, so that factor fills in the first term of each binomial. And then working with 36, we know that 6 times 6 makes 36. So that fills in the last term of each binomial. Now the only thing remaining is for us to account for this minus. It is a negative 36. So the only way that we could have 6 times 6 to make negative 36 is if one 6 is positive and the other 6 is negative. So this is the answer. But we want to check and make sure. So you can distribute x times x times minus 6. That would be x squared minus 6x. And then distribute 6 times x and 6 times minus 6. So that would be positive 6x minus 36. Do you notice here in the middle, these like terms cancel, and it leaves x squared minus 36. And that's what we had to begin with. So if you ever are in doubt about which sign to use, plus or minus or two of a kind, simply distribute and check your answer. So you don't have to memorize what to use here. So just to be clear, the final answer is the quantity x plus 6 times quantity x minus 6. In example 2, we have 16x squared minus 81. We do have subtraction, so that's a good indicator it could be a difference of squares. And then think about square root. Do we have numbers and variable terms that are perfect squares? 16 comes from 4 times 4. X squared is x times x, so that looks hopeful. 81 is 9 times 9. So we go directly to the binomials for the answer. The first term, 16x squared, was our 4x times 4x. 81 is 9 times 9. And the only way for the middle term to be eliminated would be to use one of them plus and one quantity negative. And that's your factored answer. In example 3, we do have subtraction, so it could be a difference of squares. But notice that 5 is not a perfect square, and 20 isn't either. So this doesn't look good. What are some other types of factoring that we've talked about? Maybe GCF. Do 5 and 20 have a common factor? And that would be 5. So we want to start by factoring out a common factor of 5. That leaves x squared minus 4. So now do you see how we have just created a perfect square in this quantity? That tells us the factoring is not complete. We need to keep working on it. We keep 5 as the greatest common factor, but then x squared minus 4 is a difference of squares. So that factoring needs to continue. X squared comes from x times x. 4 comes from 2 times 2. And the only way for that middle term to eliminate would be to have one quantity positive, one quantity negative. And now we have completely factored our polynomial. With example 4, we do have subtraction. 121, we know that that is 11 times 11. And x squared comes from x times x. So that looks like a perfect square already. 49 we know is 7 times 7, and y squared is y times y. So we do have a perfect square, and we do have the difference of perfect squares. So what makes this problem a little bit different is we have more than one variable involved. But our factoring technique will remain the same. We're still going to have 121x squared being the product of 11x times 11x. 49y squared is 7y times 7y. And the only way for that first degree middle to eliminate is to have one quantity positive and one quantity negative. And now we have completely factored. With our perfect square trinomials, of course, trinomial means you need to have 3 terms. So we do have 3 terms in the examples for this page. Make sure that your polynomial is in order from the highest down to the lowest power. Now, we are being concerned with the first and last term. They need to be perfect squares. So x squared is x times x. 100 would be 10 times 10. So that looks great. We also need to make sure that the middle term works out, because any number could have been put there. So let's see if this works out. X squared is x times x. 100 is 10 times 10. And somehow we need to create negative 20x in the middle. So if we don't want it eliminated, we either need to make both of these terms minus, or both of them need to be plus. So here we have a middle term that's negative 20x. That's an indicator that negative is needed in both of our terms. So if our quantities now are identical, another way to write that is the quantity of x minus 10 squared. So you could write your answer out either way, expanded or with the quantity squared notation. For example 2, we have our highest to lowest power. We notice that the first and last terms are perfect squares. So we're going directly to the factors. Think square root. The square root of 9w squared would be 3w times 3w. 25 comes from 5 times 5. Since our middle is a positive 30w, I'm filling in plus sign for both. Now let's make sure this really works. All I have to do is distribute to check it. 3w times 3w is 9w squared. Outside terms would be positive 15w. Inside product is another 15w. See how that doubles? And last, we have positive 25. So in the middle, we really are creating a positive 30w, just like we had in the original trinomial. So our factoring is complete, or you could rewrite that as your quantity square. In example 3, notice our lead term has a negative. So probably the first thing I want to do is factor out that negative, or any other common factor that's available. Besides, 5 is not a perfect square, so this would not be a perfect square trinomial the way it is written. So if I use a GCF equal to -5, let's see what happens. That would leave me a squared minus 6a plus 9. Now a squared and 9 are both perfect squares. So I can continue my factoring as a perfect square trinomial. A squared comes from a times a. 9 is 3 times 3. And the only way to match a negative middle term is if both of these terms are also negative. So I could write the answer as -5 times the quantity of a minus 3 squared. In example 4, I notice I also have negative, and coefficients are 2, 8, and 8. So at least -2 is a common factor. Then I'm going to look at the variables. It looks like m appears in only the first two terms. However, n appears in all terms. So n is a part of the greatest common factor. The terms remaining would be m squared plus 4m plus 4. Now maybe what we have here in the parentheses is a perfect square trinomial. M squared is a perfect square. So is 4. So let's try it out. Keeping our original greatest common factor, m squared is m times m. 4 is 2 times 2. And the only way to get a positive doubling in the middle is to use plus for both quantities. So that would make 2m plus 2m. That indeed matches 4m. So I would write my answer -2n times the quantity of m plus 2 squared. And now we have that one completely factored. Now here are some situations to watch out for. In example 1, we have 3 terms. We notice the first and the last term are perfect squares. So we might think, oh, we've got this one easy. Let's just think square root x times x. 9 is 3 times 3. The middle is negative, so use negatives. Look what happens when we check our answer. Distributing x, that looks great, x squared, minus 3x. Distributing -3, we have another minus 3x, and then we'll have plus 9. But look what happens in the middle. It's doubling, and that is not making -7x to match the original. This makes x squared minus 6x plus 9. So we cannot factor this one as a perfect square trinomial. It's not going to be factorable. This one is prime. And our last example, we have only 2 terms. So we're thinking, is this a difference of squares? Well, this says plus. So no, it can't be a difference of squares if it's addition. The best you could hope for here is using a greatest common factor. Does it have one? 64 and 25. Factors of 64. The factors of 25 are 5 times 5 or 1 times 25. And I know that 64 is not divisible by 5, so there won't be a common factor. So this one is also prime. If it is not subtraction, it cannot be a difference of squares. And with the perfect square trinomial, it can't be factored with that technique if the middle term is not matching. So do watch for those.